Let's consider the function f of x equal to x squared plus 5x plus 4, and we want to find any relative extrema of the function. Finding relative extrema means that we're finding relative maximums or relative minimums that the function has. From our previous videos and notes, we know to find relative extrema by first determining critical values. If a function has any relative extrema, they're going to occur at critical values. In order to find critical values, we need to look at the first derivative. So let's determine f prime. F prime of this function is going to be 2x plus 5. Now to find the critical values, we need to determine x values for which f prime does not exist or where f prime equals 0. Well, this derivative is defined for all real numbers x because it's a polynomial function. So we need to find where f prime of x equals 0. So we're going to set the first derivative equal to 0 and solve for x. So 2x plus 5 equal to 0. Solving for x, we're going to subtract 5 from both sides. 2x equal negative 5. And then divide both sides by a 2. So we get x is equal to negative 5 halves. So this is our only critical value. To determine whether this critical value is a relative extrema, we need to use the first derivative test. So to use the first derivative test, I'm going to divide the x-axis into two intervals around the critical value. So I'm essentially dividing the x-axis in half. The lower half is negative infinity to negative 5 halves, and then the upper half is a negative 5 halves to infinity. Now, in order for our critical value to be a relative extrema, the first derivative needs to change sign, either from positive to negative or negative to positive. So I've created a little chart here, and I want to determine what is happening to the derivative on each interval around this critical value. So I'm going to pick a test value to the left side of the critical value. So in the interval negative infinity to negative 5 halves, I'm going to pick a test point. I can pick any value in that interval. I'm going to choose a negative 3. If I plug a negative 3 into the first derivative, I have 2 times a negative 3, which is a negative 6, plus 5, which is a negative 1. So my first derivative at x equal negative 3 is a negative 1. So it is negative. So we can say f prime at negative 3 is less than 0. A negative derivative means that the function f is decreasing on that interval. So that is our result, that the function is decreasing on the interval negative infinity to negative 5 halves. Now let's see what's happening to our first derivative on the other side of the critical point. So from negative 5 halves to infinity, what's going on? So we need to pick a test point in that interval negative 5 halves to infinity. I can pick any value in that interval, but I'm going to choose 0. I think 0 would probably be the easiest value to evaluate into the first derivative. So plugging 0 into the first derivative, I have 2 times 0, which is 0, plus 5. So I have a positive 5 as a result. So f prime of 5 is positive. Then we have a positive derivative on that interval. So that means that our function f is increasing on the interval. So what we're saying here is that if our derivative is negative, then our function is decreasing. And then if our derivative is positive, our function is increasing. So I want to take a minute and make sure we have good intuition about what's going on here. So if our function is decreasing, it's going down as we move from left to right. Our derivative is negative. Now remember, the derivative is the slope of the tangent line. So as we are decreasing, our slopes of the tangent lines are negative. Those slopes are negative, so our function is decreasing. And then once we hit that critical point, it changes, and our function is increasing. We're going up as we move left to right. So the slopes of our tangent lines then become positive, and that's where we get the positive derivative. So our result here is that we have a relative minimum at x equal negative 5 halves, because our derivative went from negative to positive, so our function is going from decreasing to increasing. So we've determined where the relative extrema occur. Now we're also asked to list each extrema along with the x values at which it occurs. Well, we've listed the x value. Now to list the actual extrema, we need to determine the function value. So we need to plug negative 5/2 into our original function. So plugging negative 5/2 into our original function, we have a negative 5/2 squared plus 5 times the negative 5/2 plus 4, so we get a negative 2.25. So negative 2.25 is our actual relative minimum value. If we list that as a point, our x value is a negative 2.5, and then our function value is a negative 2.25. Next, we're asked to sketch a graph of the function. So in red, I've kind of indicated where that minimum point would be. The negative 2.5, comma negative 2.25. That is our minimum value. But to get other points on the graph, we can create a table and pick other x values and plug them into our function. You can choose whatever x values you like. I chose x values that I thought would be good choices around that minimum value. So for example, I chose a negative 4, a negative 1, and a 0. If we plug negative 4 into our original function, so we're plugging it into x squared plus 5x plus 4, what we end up getting is a function value of 0. And you can always pause this video and double check that if you like. And then if we plug a negative 1 into our original function f of x, we get a 0. And then if we plug 0 into our original function, we get a function value of 4. So now we can plot these points on our xy axis and then connect those points to create our parabola shape. So there's the graph of our original function f of x with our relative extrema, our relative minimum value at a negative 2.5, comma negative 2.25. We can actually check our work on this answer by using your calculator. So begin by turning your calculator on and going to your y equals, and then we're going to type this original function into our y1. So we're typing in x squared plus 5x plus 4, and then hit graph. Now my viewing window right now, if we hit window, is the standard viewing window of going from negative 10 to 10 along the x-axis and negative 10 to 10 along your y, which is fine for now. So I'm hitting graph. There's our parabola shape that we just graphed. Now to double check our minimum value and make sure that's correct, what we can actually do is go to second and then hit trace, or the calc. We want second calc. And then we're going to go down to option 3, a minimum, because we know our function has a minimum value. So I'm going to arrow down to 3, hit enter. It's asking for a left bound. So I'm going to use my arrows to move my cursor to the left side of that minimum. So I just keep moving to the left. Right now my cursor is to the left of that minimum, so I'm going to hit enter. Now it's asking for the right bound, so I'm going to move my cursor over to the right side of that minimum. It doesn't really matter where exactly, as long as you're to the right of it. Hit enter. Now it's asking if we want it to guess. So all we have to do is just hit enter again. And there is our minimum value, a negative 2.5, comma negative 2.25. Let's do another example of finding relative extrema. So to find the relative extrema, we begin by taking the first derivative, f prime of x. So taking the derivative of that function, we have a 6x plus 6x squared. To find the critical values, we need to find the x values for which the derivative does not exist, or where the derivative is 0. Since the derivative is a polynomial function, it is defined for all real numbers. So any critical values that would occur would be where the derivative is equal to 0. So let's set the derivative equal to 0. Solving for x, we can factor out a 6x. We're left with a 1 plus x. Setting each factor to 0. So we can set the 6x equal to 0 and then the 1 plus x equal to 0. Solving for x, we get an x equal to 0 and then an x equal to negative 1 as our two critical values. Next, we want to divide our x-axis into 3 intervals around those critical values. Since we have 2 critical values, it's going to divide our x-axis into 3 intervals. Negative infinity to negative 1 is one interval, and then negative 1 to 0, and then 0 to infinity. So I've created a little table here. We want to pick values in each of these intervals and determine what's happening to the derivative. So for the first interval, negative infinity to negative 1, I could pick any value in that interval. I'm going to go with a negative 2. If I plug a negative 2 into the first derivative, we end up getting a positive value. So f prime of negative 2 is greater than 0. It is positive. So since the derivative is positive, that means the slope of the tangent lines to the curve on that interval are positive. So that means that the function is increasing. So f is increasing on the interval negative infinity to negative 1. Now in the next interval, negative 1 to 0, I need to pick a test value in that interval. For example, I could do a negative 1/2. If we plug a negative 1/2 into our derivative, we get a negative value. So f prime of negative 1/2 is less than 0. It is negative. So that tells us that our function is decreasing on that interval. So f is decreasing on negative 1 to 0. Now in our last interval, 0 to infinity, let's pick a test point. I could pick, say, 1 as a test value. If we plug 1 into our derivative, we get a positive value. So f prime of 1 is greater than 0. So that tells us our function is increasing on the interval 0 to infinity. So here we have, at our critical value negative 1, our function is going from increasing to decreasing. Going from increasing to decreasing indicates a relative max. If our function is increasing, then the slope of the tangent lines to the curve are positive. That's why our first derivative is positive. And then after we hit that maximum, our function is then decreasing. So the slope of our tangent lines are then negative, and that's why our first derivative is negative. At our critical value x equals 0, our function is going from decreasing to increasing. So we have a relative minimum. If our function is decreasing, then the slope of the tangent lines are negative. That's why our first derivative is negative. And then after we hit that minimum, our function is then increasing. And that's why our first derivative is positive, because the slope of the tangent lines are positive. Our critical values, or our x values, tell us where the relative extrema occur. Now we need to plug these x values into the original function to get the relative extreme values. If we plug a negative 1 into our original function, we end up getting 1 as our function value. So our relative maximum value is 1. If we want to write this as a point, we have negative 1, 1. Next, if we plug 0 into our original function, we get a function value of 0. So our relative minimum is 0. If we want to write that as a point, 0, 0. Next, we want to sketch a graph of the function, so we'll begin by plotting our relative max and relative min points. So there's our point negative 1, 1 as our relative max, and then 0, 0 as our relative min. Next, we can choose some x values and plug them into our function to get an idea of what the rest of the graph looks like. You can choose any values you like. I chose a negative 2, negative 1/2, and 1. If we plug a negative 2 into our original function f of x, we get a function value of a negative 4. Then plugging a negative 1/2 into our original function, we get 1/2. And then plugging 1 into our original function, we get 5. And I encourage you to pause the video and double check those if you like. Next, let's plot these points on the xy axis. So there's the point negative 2, negative 4. Next we have a negative 1/2, 1/2, and then 1, 5. Now we connect all these points, and there's the graph of our function f of x.